Okay, so with that, I'd like to get started. Thank you so much, everyone, for coming, and I really appreciate it. Songwei, thank you so much for everything, for the PhD for the last 6 years. It's been a really fun journey. So yeah, with that, today, the title of my talk is Structuring Learning for Legged Locomotion with Model-Based Priors and Optimal Control. And I'll break down what this means and how this all fits into the framework of legged robotics that we're interested in most. So just to start, I want to motivate and start talking about how robotics are used today, just in industry and why people are interested in legged robots. So especially recently, there's been a lot of push toward using robots where legs can be useful. Places like environments with unstructured environments where you need to deal with stairs, with obstacles, with things that you can't really conventionally get over with just wheels. Beyond just automating physical labor, we have interest in legged robots from things like performance and sport, with these examples here, but also with assistive devices, where there's some very interesting research going on about automating and making robots for things like guide dogs to replace them and to really try and help people. So with all this, what makes robots and legged locomotion specifically so challenging? And so we have a lot of videos of these kind of incidents where in the robotics field, we kind of call them freakouts, where you have these catastrophic failures of robots doing these crazy things. And when you have something with that much torque and that much mass and acceleration, doing something uncontrollable and wild, it's very dangerous. And so we can ask, why is reliable locomotion control still difficult? It seems like we had all those curated videos in the prior slide. What's still challenging about this problem? And I think one nice way to motivate this is actually with a very old Flash game, which some of you guys might recognize, but essentially it's called QWOP, where you control this runner with the 4 keyboard, Q, W, and O and P, where each key controls one of the limbs of the runner. And the goal is to try and make him run 100 meters, but you can just imagine in your head how unintuitive it is to try and control the extension of your leg with a single button and make it coordinate in a way that it can actually run reliably, naturally, gracefully. And we have that problem, but scaled up to, that was a 4-dimensional system with 4 buttons, but now we have something with, 18, 20, like 50. These degrees of freedom get higher and higher and more challenging to control. And once we start thinking about adding hands into the loop and walking over something and grabbing something, you can see why this problem starts to get challenging. You have to constantly think about things like maintaining your balance and think about how you can really tightly integrate hardware and control and software all in a really harmonious, perfect way so that nothing freaks out like you see on the left. And so we have to deal with things like the degrees of freedom. How do we deal with perception in the loop, the nonlinearities of the dynamics, the sensor noise, and controlling contact? How we can handle things like contact when it's discrete, slippery, and uncertain at all times. So this really sets the stage for why locomotion control is difficult. And we can talk in the last 20 years about the paradigms that people have used to try and address it. And I'm going to try and address both. So on the left, to start, we have model-based methods, which I'll explain briefly. So model-based methods are a class of method where you try and use physics-based models, kind of fundamentally in principle models, to control and make planning decisions for your system. This loop that we have here is what's known as MPC, model predictive control, where essentially we have some sort of optimal control formulation. So a numerical optimization we want to solve that will give us something like a trajectory. So it'll give us a prediction of states and control inputs that achieve something that's something like what we want. It's by minimizing this cost, we're minimizing something that will get us close to a desired task, like stay close to this velocity or state or whatever. And by applying the torque, the control input at the first time step and repeatedly solving this thing, we can get something very robust and honestly like very beautiful. If we look at this example down here from Boston Dynamics, we can see these kind of tiny micro adjustments in its trajectory as it's doing this jump motion. It's constantly replanning and resolving this optimization online, and it has to do so at a pretty fast rate. 50 hertz is kind of like a minimum bar, but ideally much higher. Now, where does this go wrong? It's mainly in this optimal control formulation. Because in this optimization, we have to make a number of decisions about how we design this optimization and what models we use inside that optimization, both the constraints and the predictions that we have. So for something like this, in our x.fxu, we have a sense of this is how the physics will evolve, at least that's what I think. But in this example, which I think is really interesting, the Boston Dynamics robot fails to put this box where it needs to go. And that's fine, it's still able to control itself. But what happens is that it tries to lower its arm down to a neutral state, but it doesn't recognize that this cart is in the way, and it actually destabilizes and pushes itself over. Because that cart and that interaction wasn't modeled. It wasn't part of that system. And that's the main limitation. While they are physically grounded and very general, they build in a lot of assumptions that once they start mismatching with the real world, you're going to start to get some failure. Now, taking a step back, let's think about learning instead. Learning takes a very different approach, where instead of using any kind of physics-based principled models, you build entirely almost from scratch with just pure data. And this data can take the form of something like reinforcement learning, where you constantly interact with your environment to try and incrementally improve your policy, your neural network, to become better and better and better at doing something. Things like AlphaGo you might think of, where it just exceeds and kind of can reach superhuman performance. But also more recently, we've seen a lot of popularity with imitation data, where you try and give it expert references from something. And this could be like 10,000 people in a warehouse, all teleoperated a robot, and you collect that data and you try and train it to do something useful. This is one approach that people have used, and it works really reliably and really well. And one underrated caveat is that this network can be evaluated very quickly. It's just matrix multiplication to evaluate a neural network, as opposed to solving an optimization with something like MVC. Now, one issue that we can think of, though, is that during deployment, here's a simple example of trying to predict a function, which is just output 0 for all x. And in the range of training data, we see we can do that pretty well. We still have some error for a pretty simple function, but anything outside of that can explode and do something unexpected very easily. And so in this example, you can see how when pi theta of x is not just a number on a screen, but an actual physical torque on a robot, things can devolve pretty quickly. And that's a pretty important consideration if we want robots to interact in the real world with humans, doing important factory tasks, and to really make sure it's consistent, robust, reliable, and so on. So while they can be trained really well from data, the output can be erratic beyond the distribution. And if you don't have any kind of guidance or structuring outside of that distribution you can trust, even interpolation, extrapolation, and high dimensional schemes, it becomes a big open question about how to make this a little bit better. So if we look at these kind of, these two contributions, or these two trade-off control frameworks side by side, we can think about how model-based methods have these benefits where it is general and interpretable and composable, and we can constrain. By using the physics of the system and things that we clearly understand, variables and decision variables that we can exactly manipulate and know how they interface with each other, we can design controllers that kind of build off of each other and expand their capabilities. But being able to solve their optimization online, that is not only computationally expensive, but the underlying models that are built into that optimization can eventually lead your model astray when the real world doesn't match up. Now, on the other hand, with data-specific methods, we kind of lose these benefits, where our data makes our policy, our controller, our neural network very training specific. And our network is more of a black box that's monolithic. We can't easily take a controller from one robot and apply the exact same framework to another robot. There's a lot of kind of specialization and fine-tuning that happens with neural networks. And we lose guarantees of being able to constrain, no matter what, do not do this kind of thing in your state space. We lose that guarantee. But on the other hand, we have gained a couple of benefits in terms of how quickly we can evaluate these networks. And we can train policies to be very robust because they have no model built in. With all the data, we can include data of things like bumping into things or experiencing different slippery floors and objects and a wide variety of states that make it really robust within the data distribution given. So a lot of my PhD work has been about kind of this blend and this combination of the two. And that's where I really want to start talking. So the kind of theme of my thesis has been about how we integrate learning with model-based priors. And I'm defining model-based priors pretty loosely in terms of model-based quantities, methods, techniques, and controllers specifically. So here's a couple of highlights of the results that I collected. The question I want to think about for this talk is how do we design constrained, interpretable, scalable controllers by blending model-based control with learning? So with that, I want to get started on my 3 projects, and this is an overall outline of the 3. And I'll start by talking about the first, which is constraining learned controllers with MVC. So I wanted to think, oh, sorry. I wanted to start by thinking about specific tasks, like what's a task that we want to solve with, just a robot in general. And when we have those tasks, what do we have to pay attention to? And I kind of call this a hard constraint task. This is a recent example when Alex and I gave a demo at CSAIL of the mini cheetahs, and all these little kids that passed by started swarming the mini cheetah as we were walking it around. And I remember trying to avoid them and trying to get out of their way. And it got to a point where they would come right up to it and try and touch it. And I had to just stop because I was terrified that, it would like hit one of them, or they would run into it, or they would kick it over and it'd start freaking out. But there are tasks where we have a, absolutely, we must satisfy some state-based constraint. And to not do so, it means some loss of life, some important damage, something that cannot be done. And if we think broadly beyond the scope of where robotics could go, like when we have robots in the home, when we have robots in kind of unstructured situations, we have a lot of these kind of hard constraints we need to pay attention to. Don't hurt yourself, don't hurt other people, laws of robotics, that kind of thing. So we try to think about a situation that was extreme. We flipped this guy on his head. So one scenario we thought about was about a falling robot, where if you have some robot that falls off a table, off of a disaster site, whatever, we have two important constraints we need to satisfy, which is we need to be able to plan that online very quickly because we're in a fallen state. We need to recover so that the robot can stay safe. But we also have to guarantee, we have to somehow make a plan that guarantees that it satisfies those constraints, which is survive, keep its body height above the ground, keep the forces reasonable, and so on. So how do we do this? Let's start with from the model-based perspective, where we can make an optimization to try and do this. And so I won't go into the details unless people are interested, but we can formulate this optimization that's very complex and try and design a alignment controller for this, for our mini cheetah, for our little quadruped system. And when we do so, we get some pretty nice trajectories. We get this really natural looking motion. I initialize the robot from some initial angular and linear velocity, and I can get some nice trajectory of it safely recovering and in a reasonable, survivable way, obeying all the physical constraints of the system. But it takes anywhere from half a second to 5 seconds to solve this optimization fully. So the question, if we visualize the results, we can get all of these guys from a variety of different initial sources, and we get the motion that's, pretty nice and natural. One I really like is this one, where it falls straight down, but actually twists its legs to kind of dissipate the torques that we need to have. So we have very realistic motions from this, but it's very, very slow. So the question we wanted to ask is, how do we solve this optimization faster? And in an abstract sense, what we can think about is to solve an optimization, we can start from some uninformed initial guess, and this is the cost landscape of that optimization. We want to follow the gradient down to some local minima. That's how we solve an optimization. If we don't have a good sense of how to start this problem, we're going to start from somewhere arbitrary. Let's say all zeros are a guess. And when we do so, we take a long time to finally find where we need to go. But suppose we had some sort of really good warm start, where we had some good sense of what the solution should look like. I have a vague sense of how my quadruped should land. Like I've seen cats and stuff before. And so if we started with this warm start that was very good, we could start closer to the solution and solve it faster because we don't need to travel as far. And so that's really where we started to think, well, I have a lot of these direct optimizations, and at least offline, I can solve them all and collect a bunch of data sets. And can we use this somehow to learn this warm start? And that's what we tried to do. So based on some initial sampling, some sampled falling state of the pose, the initial linear and angular velocities, we can solve this direct optimization and add it to our big data set. And now what we want to do is train a network to be able to reconstruct this exact trajectory. And so here we actually have two different trajectories. This is from the learn policy, and this is from the optimization. If you have sharp eyes, you might notice that this very slightly has wiggles and doesn't quite obey the contact constraints, but they're very, very close, at least visually. And in state space, of course, they're quite close too. So we can train a network to almost exactly reproduce this, but it doesn't satisfy the constraints and feasibility of our optimization. Because how could it? It's a neural network. There's no real way to guarantee or build that in. Though that being said, there's a lot of interesting research happening on constrained learning. Professor Lee probably speaks about it. But this is what we do. And so what do we want to do with this? We have our learned warm start, and let's see what happens with it. With our sample falling state, we can evaluate our warm start first, and this is pretty much, in a sense, pretty much for free. We can evaluate this very quickly, and we use this to learn our optimization. And when we deploy this on the robot, this kind of solve times that we see are like this, where the learned warm start here is how much faster we get compared to the cold start. So we see almost an order of magnitude or two speed up in terms of how quickly we can solve this problem. And we go from about 0.1 to 0.5 hertz to 10 to 20 hertz, which for developing just a general plan is fast enough for a falling controller. And that is what we try on simulation and hardware. And so we actually deploy this and we see simulation, in simulation, everything is nice and smooth and perfect without state estimation. But trying on our hardware, we see that we can actually do this in real time. I was very careful to try and hold it exactly level because I had no good state estimation when it's off the ground. So that's what I had to do. I will also say the first time I tried this, it didn't work whatsoever. And it just clattered into the ground and it started smoking. And in my first 6 months of grad school, that was a terrifying thing, but it was fun to see it deployed. Yeah, so with that, we kind of want to wrap up with our conclusion and takeaways for this project. We had our robot state and we evaluate this policy, this learned network that gives us a warm start, which is then fed into an MPC. So at a higher level, what this does is that we can develop some approximation of what our motion looks like from a learned neural network, from lots of data, whether that's from MPC or from wherever you source that data. But by making sure that it's passed through a final optimization layer, you can ensure that it satisfies constraints. And it's projected onto things like equations of motion, dynamics, torque limits, all these things that we might want to care about, and don't hit the child, for example. Yeah, so what we've done is we've combined these advantages in a hierarchical sense. So next I want to move on to the second project, which is about computing model-based priors at scale. And so to talk about this, let's revisit what we just discussed, which is this pi landing. I have this policy that has, and let's just say it's perfect. It can exactly and instantaneously recreate the MPC solution. The problem is the performance of that policy will never exceed MPC in general. It will always be limited to exactly copying it, even at its most ideal. So what we can turn to is something more like reinforcement learning. And this is where we kind of have seen superhuman performance and speedups with things like AlphaGo and chess and StarCraft and Dota and all these things. And the way reinforcement learning works is by improving through large-scale environmental interactions. This little visualization shows how thousands of robots are deployed and computed in parallel to all, collect data on how to interact with the world. And slowly over time, it can collect a lot of information on how to improve the control iteratively. Now, the problem is that most of these schemes and most learning schemes in general are really data intensive. So for this example, for reinforcement learning, it relies heavily on performing the computations entirely on the GPU only, and by parallelizing the simulations and the gradient updates. And the scale of this parallelization is typically anywhere from 1,000 to 10,000 environments. So if we wanted to bring model-based things into this kind of environment, we have to compute model-based quantities, model-based priors, controllers at the same scale, anywhere from like 1,000 to 10,000 model-based controllers at the same time as efficiently as possible. So can we do this? Well, a lot of researchers have had a lot of interest in doing this kind of thing. And a lot of them have been interested in trying to bring in model-based controllers into learning. And the way they did it was similar to how I did it originally, where you compute data sets offline and you try and bring that into a learning environment, purely from the data alone. This first example, this citation one, was called deep tracking control. And they tried to do it at the same time, where they would compute model-based controllers on the CPU, transfer that data to the GPU, do a learning update, and transfer that data back and have this kind of cycle. But the policy took weeks to converge. And I don't have that kind of time for grad school. And I don't have that kind of compute for grad school either. The computational architecture needed to handle this required like huge clusters of CPUs, which, let's constrain ourselves to the setting of having one desktop environment, a 3090 for the last 5 years. So if we think about what makes this hard, if we have some sort of model-based prior that we want to compute, we could just try and do it raw, with the tensor algebra, with PyTorch, with libraries like this. We could try and compute this for, let's say, 10,000 environments. But it quickly gets very difficult to try and manage all this bookkeeping and to keep the correct dimensions. And every single implementation will be tailored for a specific algorithm. Similarly, if we could just do this naively and just do this in serial 1,000 times, we could do that eventually, but that's even more inefficient than leveraging any kind of parallelism on the CPU or not. Why not just do this transfer? The main bottleneck here is that when we separate our computation on the CPU and the GPU, copying this data between the devices is the main bottleneck and what takes so much time and makes training so inefficient. And lastly, just approaching CUDA in general is, I would say, it's not beginner friendly. People who might be interested in doing this ideally would not have to learn CUDA in a separate programming environment to be able to implement their algorithms efficiently on the GPU. So a lot of this has kind of been barriers to entry for how to handle this integration of model-based priors for learning environments. So the next question we wanted to tackle was basically, how do we scale this up? We have model-based controllers that we want to scale from at an RL level, 1,000 to 10,000. How do we actually make this more efficient and compute them in parallel? And that's where my second project, Kusati, was kind of motivated by. To start, let's assume that we have some sort of model-based prior that I want to compute many times. I want to compute this function 10,000 times. And you can think of this as f of x is equal to some MPC controller. But for now, let's use a very simple example of this function. So the first thing we can do is atomize the expression. And what that means is we want to break this down into elementary operations like sine, like plus, and square. And this is a symbolic expression. We can exactly recreate this function by breaking it down into these constituent elements. And this is what Kusati does, a symbolic frame. The next key ingredient is to do vectorization. So each of these operations that I mentioned, sine, plus, and square, each of these can be vectorized on the GPU. And that's where the speedups of GPU are really born, where you can compute sine of x for 10,000 environments simultaneously on the GPU and really get a lot of efficiency here. This is what's known as a CUDA kernel, which is just a low-level GPU kernel. And I can make a CUDA kernel for every single one of these operations. I can make a vec plus, a vec square, a vec sine, and any other operation that we can find out. And lastly, we have to keep in mind that we can evaluate f of x by just running through these instructions sequentially. So I start with x, and then I do my vec sine, my vec plus, and et cetera. I can keep going for as complex as this function is. And with 10,000 environments, all of these will be vectorized all together at the same time. So that's kind of the key to Kusati, where if we have the symbolic expression on the left, we can then evaluate a batch of inputs by having a batched operation of sign, a batched plus, a batched square, all in the GPU, and get a batched output set of outputs entirely all in the GPU. So we can automatically code generate CUDA kernels, and that's the tool that we developed to try and cross this bridge and address this tension between the model-based and kind of learning-based worlds. So by doing this entirely in the GPU, we have entirely cut out that transfer of data necessary between the CPU and GPU. And we also developed this bridge for compatibility with the learning environments. One of the things that made me happy is when Joris Gillis, the guy who created Kusati, he says, the MIT paper below introduces Kusati, well played. And I appreciate that because I thought a lot about this title. Yeah, so if Joris is watching, I really appreciate it, but I don't think he is. We'll move on. For benchmarking, so this is what we did to evaluate speedups of Kusati as a tool. And this is just 0. We have no speedup over a naive evaluation. And so we see that, we have a pretty significant speedup for Kusati across all the ranges. On the x-axis is the batch size, so how many in parallel we're trying to evaluate. And the symbols denote how complex the function is. By complexity, I mean how many instructions are required for that function. So for this simple example, we have 1, 2, 3 instructions, but you can imagine for something like MPC or computing centroidal momentum or something, this becomes a lot more complex. So as the function becomes more complex, our speedup, our benefit of our speedup decreases. But at the scale we care about for reinforcement learning, between this 1 to 10,000 that I mentioned, we still have a speedup of around 10 to 1,000 times based on how complex the function you're evaluating is. So we have this nice mature tool now. Let's go through some examples and applications of how we can use this. One example is with this drone. Let's say I have a stationary drone, equip an LQR controller to it, and I want to characterize how good is this controller. I want to kind of do like a characterization of the controller, and I want to disturb it with some impulse initially. I can write a symbolic function that is a simulation step, and I can parameterize it based on something like a thrust. I want to evaluate this controller for 5 different drones, each of them have different thrust limits. When I do that with Kusati, I can parallelize this very trivially. And I can explore what I've been hinting at is the region of attraction for the controller. Based on how large my angular and linear momentum disturbance is, from what are the ranges of those disturbances that I can recover from with this controller. I can evaluate this very simply across the thrust limits that I have. And we see this very interesting plot for the region of attraction. Another example and application is using centroidal momentum in reinforcement learning. So this was interesting. This was a prior work from Professor Patrick Lindsay, professor at Notre Dame, who studied how by using centroidal momentum specifically in an optimization-based framework, you could get emergent arm motion for motions that required a lot of centroidal momentum. Motions like kicking or walking, you could have these arm motions naturally emerge. Now, for RL work, typically people have used the base angular velocity to try and do velocity tracking tasks, where if you want to turn sideways, you only care about the angular velocity of the base. And they paid less attention to things like the centroidal momentum or the angular velocities of the arms. So we thought, instead of rewarding the base angular velocity, what if we incorporated centroidal momentum into this and do some RL? What kind of locomotion do we see? And we actually see the arm motion appears pretty naturally as kind of anti-parallel to the motion of the legs. And it really, Hojay, the audience right here, he extended this work in a fantastic way and just to incorporate this even further. And we developed this walking controller where on hardware, you can see this arm motion quite naturally as well. Now, quickly, I want to talk about how we can use this for control and whole body control specifically. If we have some sort of constrained whole body controller for a manipulator, again, with Kusati, we can parallelize this across all the environments and just simply learn the higher level policy, which is, I have a controller that can move arbitrarily in space. Let's learn an RL controller that tells me how to move to grasp something. And this is, again, another work under TRO submission that we submitted pretty recently. I'm very happy about. Now, lastly, if my interest is primarily in locomotion, so my main concern was about how we can parallelize this. I have some sort of MPC controller that I want to parallelize with Kusati, and so that's what we did. Across all these environments, I have this parallelized controller now. Now, that's where I want to continue to transition and talk about my final project, which is actually learning the residuals to MPC. So we've started with thinking about, model-based priors are difficult to parallelize. We developed this tool, Kusati, to try and make them easier to parallelize, and now we have. And we have this now in learning environments at the scale that we care about for learning. And so on the right here, we have an algorithm. We have the flowchart for how we can, how reinforcement learning works. All the parameters and rewards and flow of data that we need. But the open question is, how exactly do we place this GPU parallelized MPC into this algorithm? There's a lot of design choices here that we have to make. For example, we could use the MPC as rewards in the environment and say, hey, our policy, I want you to try and copy the MPC rewards. It's not a bad idea. It's kind of an expert controller in a way, and it'll get you pretty close to what you want. But if you, like before, if we exactly copy that, then we're not really going to exceed the performance of MPC unless we add additional rewards that it can try and get close to. We could include it as part of the training algorithm, as I've seen some people do. Like Cacto is one paper also from Patrick, where you can use the value of MPC to try and guide the training and inform when you're doing well and when you're not. But the direction that we chose is actually trying to integrate it directly into the policy. And we do so by using something called a residual architecture. Basically, we can evaluate the MPC. And so if this bottom line alone was all that there was, that would just be a typical MPC controller. But we can actually learn a residual network on top of that. So a small learned adjustment to our MPC that could help when it's out of distribution, when the MPC starts to fail. And so philosophically, what we have is this kind of core model-based controller, which is physically grounded and retains the benefits of model-based things. And we try to learn this layer of corrective torques on top of that. So with this in mind, we have our three situations we want to compare. We have our only MPC, we have only end-to-end, just a pure network that we're training with RL, and our residual situation. And we give all three of these the same rewards. It doesn't matter that we give this one any rewards because it's a fixed controller, but we are essentially comparing these two. And so giving these two the same rewards, we wanted to see how does this performance kind of change. And so when we look at the reward curve after training, for many hours on the GPU, this is what we see. One thing I want to point out is that the residual policy immediately jumps up to a pretty high reward, actually to the baseline level of the MPC, because that's where it starts. With the zero initialized network, you're going to exactly start with your MPC performance with a little bit of policy noise. So your performance immediately is going to be at a high baseline level. So you get some sample efficiency benefits there, but it's still overall, I would say, not a huge difference, right? I mean, they converge roughly to around 12 to 13. Even asymptotically, our residual is a little bit higher, but at a given fixed iteration count, I would not say within noise that there's any difference between these two. So the residual is more sample efficient, which is expected, but the return seems similar. So how is this performance actually different? When we look at it qualitatively, this is the kind of behavior we see. With the end-to-end policy, we see, in my opinion, something that's quite typical of reinforcement learning, where without enough guidance from the reward, it's going to learn to do something that abuses the physics of the system, of the simulation, pretty quickly. Whereas with the residual policy, you see that it stays pretty close to MPC. It's taking, natural steps. It's taking the motion, I would argue, is a lot more physically realistic, but you still see behavior that's a little bit different. You'll notice that if we play this again, that it actually exhibits some heel-to-toe behavior, which is not possible from the MPC formulation. It's been exactly constrained to not do that, but it can learn corrective torques that adapts the foot to and the ankle strategy to adjust a little bit that way. And if we analyze this performance in a more quantitative sense, we see that the residual policy in general is much more nicely tuned to a physical, realistic deployment than the end-to-end policy. Like deploying that rapid tapping behavior, I would not really trust without a lot of validation. And if we look at these metrics like the power, the ground reaction forces experience, the joint torques, the joint velocities, we generally have a smaller, narrower spread from the residual policy, which is ideally better for hardware deployment. So that brings up an interesting question, which is these policies were both given the same rewards. They have the same gradient signal that they should try and follow. Why did they converge to such different behavior? And so to try and explore this further, we look at how the policy converges through a tool called UMAP, which is a dimensionality reduction technique to try and analyze high dimensional data. So what this does is, this example is like a 3D point cloud of a mammoth with labeled data sets, like these are the tusks. And it pushes, once you push it through UMAP, you have two-dimensional data. And you can see how local structure is preserved in this mapping. And so things that associate closely with each other, like the tusks, remain close in 2D space as well. And that's just a dimensionality reduction tool to help visualize things. So we wanted to explore, can we do this for the humanoid and just track its states and distribution of states throughout training. We have a 48-dimensional state vector for the humanoid, and we want to convert it into 2 dimensions and just visualize that on screen. So when we do, this is what we see. We have our distribution of states from the end-to-end policy at the very start of training, iteration 0. We have the distribution of states from the MPC controller level. These are the same because they're all initialized in the same way. They all get the same rewards. So the distribution of states we see for the MPC is the same across both of these. And the residual network is initialized to be near 0. So the distribution of states for the residual policy is also equal to the MPC. because in the start of training, it's essentially outputting very, very small values. So it's going to stay very close to MPC. Now, what happens when we explore this throughout training? That's what we see, where the distribution of end-to-end networks follows the gradient. It follows how it wants to be trained from the rewards, and it ends up in this kind of cloud over here. Whereas the residual policy really starts to take on the shape of how the MPC was initialized to be. And so our conclusion here is that the MPC very clearly, it biases learning and it guides learning toward a more desirable state. Even though it's been given the same rewards, we have a very clear distinct behavior and qualitative differences between these two. And so initially, our first project was about warm starting an MPC controller. And here, in a sense, we've actually warm started the training by using a model-based controller instead. So now what we can do is we can look at some interesting aspects of its performance. One behavior that was really fun to see was that for MPC formulations, self-collision is a very challenging constraint or cost to try and implement. It's very nonlinear, and you can imagine how, depending on the morphology of a robot, it can get pretty tricky where this is valid, but a slight variation on that could hit your body. Additionally, having that kind of cost, it has to be differentiable, and you have to solve this online constantly if you're going to do that. Whereas in reinforcement learning, by giving it a reward, this can actually be very discrete and simple. You don't need rewards in reinforcement learning to be differentiable or formulated in a specific way to be optimized online. You can just simply have a binary. If it hits itself, just give it -1. Don't hit yourself, and it'll learn that over time, despite this non-differentiability. So what we see is the situation where the MPC, when I have it turning in place, it does self-collide. It's able to stay stable, but it hits its knees together right there. And it constantly does this throughout time. Whereas the residual policy on the right learns this behavior for the exact same command and state that it's been initialized in. It learns to keep its body a little bit more upright and actually adjust where it's stepping on the ground so that it doesn't hit its knees together. And we can plot this directly. The dotted lines are the penalty for self-colliding, and you can see the residual is 0 for all time here on the left. Whereas the model-based controller, you can see at consistent intervals as it keeps turning, it has that high penalty from hitting its knees. Yeah. So interestingly, the residual learns to adjust the MPC behavior as we kind of theorized. It learns corrective torques to obey things that are beyond the scope of what the MPC costs are. Another interesting aspect was about how it could generalize to different things it hadn't seen before. I made a big point about how outside of the training distribution, it's unclear what the policy can do, but now with this MPC structure, what we see is something interesting. We train the policy to it has only ever seen the MPC doing a fixed gate, which is a very constant and unchanging sequence of periodicity of stepping on the ground. But when we modify this, after it's been trained, we see that it can actually adapt to this quite well. Even when we command a double stance phase where the feet, you kind of have some heel-toe stance at the same time, or a flight phase where it's hopping from foot to foot, it's able to still walk and do that locomotion, whereas MPC fails to do so entirely. Of course, we can tune that MPC to work for that specific kind of gait, but there's no guarantee that it will work for everything else. Something else we tried is exploring more about terrain. So what we did here is it has only ever been trained on flat ground, but we decided to give it some sort of disturbance. I'm going to slow this down actually. And we decided to give it some sort of uneven terrain. And while the MPC fails, the residual is able to handle this, even though it hasn't been seeing this before. This is a fun example where there's a very clear high step where the RL policy is able to do this tapping thing, but these two get caught. After training, we can still modify the parameters of the MPC and then modify the parameters of the MPC to step just a little bit higher so it can clear that gap. And after doing so, it can clear that exact gap quite nicely. Of course, this is like a pretty cherry-picked example. Like I've specifically chosen the situation where it has to step higher to cross this gap. But the point is that after training, I don't need to go back and retrain the policy to handle higher steps. I have this tunable controller at deployment time to adjust its behavior. And this tunable controller is not something that's learned where it might go out of distribution. It's a model-based controller where I have very firm and clear grounding on how it works. Yes. So finally, we deploy this to hardware and we see, since real transfer efforts, one thing that was pretty fun is compared to Charles's work, which is what the MPC in this work was based on. His controller had a very hard time stopping, just stopping motion, and being able to start walking again after that. This, for some reason, worked much better for that because those situations could be trained in that environment. It was always a weird quirk of this controller that I never quite understood why, but it was also something interesting to see that it was able to handle those cases where it stops and is able to restart. Yeah. So our takeaway from this project was that, hey, we were trying to overcome limitations of our PC and try and see if this kind of architecture can give us any benefits. And what we saw is that this embedded MPC can really help guide policy training. So if we only, I'm a pure learning guy, I only want to deal with data, I can still use this to try and guide policy training and not have it be part of the final system. I can kind of wean that out and wean out the effects of the MPC. And as it gets guided to a good local minima, say, take it away completely and say, okay, now keep learning. That's already one good benefit of having this. But when we have this in this kind of residual architecture, we see that it clearly provides robustness to features that were unmodeled in the MPC. It has never modeled uneven ground in that way, and even trying to model uneven ground in a model-based context is very difficult. If you have some sort of weird gradient and you have some sort of height map that can be noisy, a lot of that introduces problems from a purely model-based standpoint. But from a learning framework, that's actually quite easy to. And lastly, we saw that the actual benefit of the MPC from the perspective of the network is it really helps generalize. It's able to extend its capabilities beyond what it's seen and experienced in training because it has this model-based backbone that's able to do things like, oh, I can exactly reason about where I want to step, how high I want my foot to swing. And these are not things that need to be explicitly trained with lots of data that could be susceptible to, all sorts of out of distribution issues, but it's something foundational that I know will work. So as my summary, I wanted to kind of end with this takeaway. For the first project, we had this warm start that was then passed through a constraint MVC to ensure that it's able to satisfy constraints that we care about in tasks where the constraints are very, very critical. Because of that integration, we wanted to think this was all performed offline and collecting that data took a long time. How can we speed this up and really try and embed model-based methods directly into GPU, directly into environments where learning can have has a firm advantage? And lastly, with that parallelized MPC and those parallelized model-based priors, we wanted to explore how we could use this for RL and really try and integrate this more tightly and see what complementary benefits they might have. And so as a takeaway, kind of the philosophy that Sangbei has, he's used the phrase brainwashing a couple times during my PhD. I do think it's accurate. I think that my philosophy in general has been like, you should try and always model what you can and learn what you can't. There's a lot of things that we can't model, but there are also many, many things that we still can model very well that we should just abandon because we have new tools and new data and new frameworks that people have been pushing forward. I still think that philosophy, I still believe in that philosophy. And you talked a little bit in the beginning about how after coming back from micro, I was a little stunned by how good the learning models are. And it's fair. I still think they're quite amazing, but I think I've started to see some of the progress and recent developments with pure learning frameworks, and I don't think it's the answer. I don't think it's the only answer. That's not the only way forward. Yeah. So that's a summary of my presentation as a whole. I just want to wrap up a little bit here. This is a small contribution, these three works out of like a much bigger picture, a bigger story with collaborations with other people, some of my work, and a bigger picture overall in terms of legged robots. It's definitely not the only way of going forwards. And so everyone who's worked with me on this, I really want to appreciate them and give my thanks for their contributions toward this stuff as well. Awesome results overall from hardware as well. Yeah. I want to thank my community members, of course. Sangbei, for the last 6 years, you've guided me and you took a chance on me, I would say, when I first applied on that Zoom meeting. I knew very little about robotics at the time, and I was actually thinking about joining Professor Hunter's lab because he had emailed me the week before. But I decided to wait, and I'm really glad that I did. To my community members, everyone, I really appreciate, and I want to thank you guys so much for being so positive and supportive. I was expecting a big fight and a big convincing of my work is valuable. I swear, I'll do anything you guys want. But you guys were very supportive and gave me resources and links and things that made me really change my perspective and think more about the kind of research that I do. Yeah. I want to acknowledge my family, of course. And, I don't think I've shown anyone really pictures of my family in lab, but here they are now. My sister and her cat, my mother, my parents, my grandma, my other grandma. Yeah, just in Korea, they've always been so supportive of me, and I really appreciate that they, I don't call enough, and they're okay with that, and they just try and gently remind me, please call more. That they don't do more than that, and I really appreciate that they have always supported me without question. I am not a guy who takes a lot of photos, and yet I still found so many, and I couldn't even include them all. If you're not in this, please know that I haven't just ignored you. At some point I had to draw a line with space. The lab is a really unique culture, and we've talked about it a lot, but we hang out with each other almost way too much, where other labs I've heard is much more like a 9 to 5 where they just work and they kind of go home, but we've done so much together. And I would say most of my close friends at MIT are just purely from the lab. And I don't need to meet other MechE students really because most of them have been in lab. that being said, there are, of course, people here that aren't just from lab, but so many, here's Danny from a long time ago, and Mang. Here's people who aren't in the lab or from MIT, and just all the stuff we've done adjacently. Great picture of Yanran and Chanel. Yeah. And finally, of course, the friends beyond MIT. I don't think it's good to get outside of the MIT bubble in general. I think not always to stay and always be associated with people who know your research and know your work. And this is again pretty recent. Volleyball tournaments. I had one yesterday, lost again. As is normal. My friends outside of MIT, from undergrad, from high school, and this is just a random group that we formed over summer for an intuitive internship. Yeah, I mean, thanks to all you guys, I was able to just stay sane and keep being encouraged to keep going here and to push through. Yeah, so with that, I'd like to conclude. This is my summary overall of my research, so please feel free to ask a question. But thank you so much for listening.